Good morning. Hope everybody's doing okay. Over here, it is lightly snowing this morning, um, so that's super fun. Hope you're all staying warm, um, having a good Friday. Today, I'm going to do some office hours, so if you have any questions or things like that, go ahead and drop them in the Twitch chat. Um, I will say, though, that what I want to start out with first is actually going to be looking at some stuff that maybe doesn't get talked about as much in YT. So specifically, I'm going to show a couple of the interactive visualization tools that we use, or that we have. Now, both of these are currently packaged outside the main YT ecosystem, or the main YT repository, and that allows them, in theory, to update at a different scale and or a different rate, and to let us move more quickly and so on. Whether or not that actually happens, I guess we'll see. The proof will be in the pudding. I'm going to go ahead and switch over to the main view for today. And we're going to start out with a brief overview of some of the things you can do in Jupyter Lab. So switch over to coding. All right, there we go. So in Jupyter Lab, there's a rich ecosystem of widgets and so on that you can utilize. YT provides a couple of those built in to make some of the things that you do in analyzing data a little bit easier. And I'm going to show those real quick. These come with the basic YT package. So if we do import YT, that gives us our standard YT system. And then I'm going to load up my favorite data set, and maybe it'll be your favorite data set too, called Isolated Galaxy. And what Isolated Galaxy is, again, is just a basic Isolated Galaxy data set. And when you access data sets in YT constructs a set of fields that it knows how to generate. It constructs a set of fields that it recognizes on disk. And then what it does is make access to those fields pretty straightforward. You can access them just as though they were real. So whenever you ask for something, if it doesn't exist on disk and YT knows how to make it, it goes ahead and generates that on demand. So I'm going to go ahead and show you, but one of the problems with this is that it can get a little bit overwhelming. There are lots and lots and lots of different fields that are accessible to YT, so knowing what they each are, their various different characteristics, and so on and so forth, can be a little bit overwhelming. So built into YT, we provide a field explorer. So if you just type ds.fields, what comes back to you here is this all field, deposit, enzo, gas, index, IO, and nbody. Those of you that have used this data set or data sets like it before might recognize these as being different types of fields. So for instance, all of these enzo fields are the actual fields that exist on disk. So when I choose one, you'll see that it shows me the source, and in this particular case, it gets a, oh, hi Stuart, nice to see you. This gives you a set of the source for how to define it. Now for all of the enzo fields, these are all fields that exist on disk, and that's why they're called enzo. But for field types like gas and so on, you might have something like EL fraction, EL mass, and what you can see here is the actual source code on disk that generates them. In some cases, this isn't going to be super duper useful. But we also provide a little bit of additional information here. So for instance, if I look at EL mass, so that's the electron mass, it shows me that the mass function is defined this way. And it says data F type, and this is an F string, so a special type of formatting string, and then it multiplies it by data index cell volume. If we look on the variables tab, you'll see that here it shows all the different variables that are defined inside this closure. So when YT generates this field information, it looks at the different variables that are defined inside that closure so that you can sort of fill in the blanks. And that helps a lot when we're looking at something like HE number density, because HE number density, helium number density, is generated inside the field definition itself is generated inside a loop. And inside that loop, it's looping over different species and suffixes and so on. And so we can look at the source code, and then we can take a look at all the different variables that are defined inside that source code. Now, if we look at something else, like say kinetic energy, if data.ds.fields detected, you can see this is a deprecated field. If we look at kinetic energy density, you can see here the source code is a little bit more useful because we see v is equal to obtain relative velocity vector, and then it's taking the sum of, or it's taking the magnitude of that and multiplying it by the density and then cutting it in half. So that is the kinetic energy density. So just by browsing these various different definitions, and you can see here metal density over density for metallicity, it's got an F-type, but that's not super useful. We can look at the various different definitions. Here, let's take a look at an interesting one. So if we wanted to look at the vorticity growth along Z, you'll see that it returns the negative vorticity stretching in Z minus the baroclinic vorticity in Z. Looking at the vorticity magnitude, you can see that it sums up the squares and then returns the square root. So just by doing this, we can dig in and see things a little bit more in detail so that we know what we're able to utilize. So there are a couple other things that that YT also provides in terms of Jupyter widgets in the base distribution, but where it really starts to where we really start to have fun with it is if we start to look at a package that currently is not distributed with YT, that's called widgets. So I'm going to show you an example of using widgets, and this is what's called a dataset viewer tutorial, the dataset viewer. So I always have to remind myself of the way to see this. So I'm going to go back over here into my notebook. We can import widgets. And you'll note here that in what I generously would refer to as a delicious pun, we call widgets widgets with a YT in it. We can import it. And then we can create a dataset viewer. So we'll call this ds viewer is a widgets.dataset viewer, where we specify our dataset is equal to the dataset we were looking at before. Now, I recognize this is a little bit clunky. If you're actually doing a whole bunch of dataset viewing and so on, it probably makes sense that what you would want is you would want this to just be the default way. So for instance, if I type ds, it shows me, oh, Enzo dataset. It would be a lot nicer if the default dataset viewer actually were this widgets dataset viewer. But we're not enabling that at the time being. So we can say ds viewer is equal to widgets.dataset viewer. And if we type dsviewer.widget, what we come back with is we come back with a whole bunch of cool stuff. So here, this is the entire grid structure for the dataset, and it's embedded using Py3JS. We can go through here, and you'll note that there's a bunch of these sliders and so on. For the most part, I haven't found these to be super useful, but it felt like the appropriate thing to do. We can turn on and off displays of different levels. So here we've got level 0 on, along with level 6, 7, 8. And I'm scrolling in, and you'll note that the clipping plane gets a little bit funny. That is likely to happen with AMR, but unless we do some clipping plane adjustment, which we don't. And then it adds this. Now, ideally, this will eventually be usable as a mechanism for constructing paths. So we've got this ability to do keyframes and switching between them, but it doesn't quite work. And one of the reasons that it doesn't work, I think, is that I'm not able at present to figure out how to get the full camera state out of 3JS. But we'll take a look at that another time. Now this also embeds into it all of the different fields. So the exact field viewer that we saw up here is embedded here, and I can go through and see all these different field values. And because we're dealing with data sets that are composed of large amounts of metadata and so on, we also make it accessible to look at the metadata. And so this is a drop-down widget here where we've got the entire metadata of the data set. So in this case, it's 1,000 lines of Enzo metadata here. And they're embedded in this, and in some cases it's even nested because it converts it into JSON. But I can also type into my filter here, let's say I want to look at co-moving coordinates. I type in co-moving, and I guess it doesn't filter it. Oh, you know why? I bet it's only filtering the top level. Anyhow, we'll take a look at that another time and see what we can come up with. Oh no, it does, it highlights, but it doesn't filter. So that's something that you can potentially utilize. Now, one of the other cool things that I like about this is it gives you the domain left edge, right edge, and width. And then because these are all unitful arrays, you can ask it to convert them into different units. And so if I do AU, you'll see it tosses it out in AU. Although, what use really is a galaxy simulation that's in AU? And I think if we do something like domain width here in the notebook, yeah, it'll do it there as well. Any three tuple, length 3 unit array that gets displayed here, I believe, gets tossed out with this. So we can see it in smoots or in yards, and it's a bit of a fun thing, but not incredibly useful. So this is the basic stuff that you get with widgets, and I find this to be pretty useful, this display, just so that I can get an overview of the AMR. And we've got it set up now so that in principle we can export these to either the hardware or the software volume rendering, but it's not as easy as I'd like it to be, and so hopefully that'll be something that gets addressed in the future. All right, so that's the dataset viewer inside widgets. But what really makes widgets useful for interactive exploration is the ability to do what I guess we could call slippy maps of dataset viewing. So I don't know how many of you that are watching. I mean, I see how many people are watching. I don't know how many of you remember MapQuest or the days before Google Maps. But back in the day, you used to be able to see a map, and then you would click on something and it would refresh and you would see the next tile over. And then the invention of Google Maps, this slippy map where, in a sense you could touch it and move it, brought a real tactile nature to it. And it also really improved people's ability to see the data that they were dealing with, in that case maps. So we provide that inside our dataset viewer, or inside our widgets package, but we build it on top of the existing methods in YT for viewing two-dimensional map-like data. So for instance, when I make a slice of something, I do something like s, so that's my slice, is equal to ds.r. And ds.r is something that I think people don't necessarily see that often, but it's one that I'm really fond of, because it's a fast way to reference and select data. So you can choose ds.r and you can specify to it, as though it were a sliceable object, different specifications of where you want to grab the data. So let's say that I wanted to slice along the z-axis. The z-axis is our third axis. So I'll take everything along the x, everything along the y, and I want to slice at 0.5 along the z-axis. So our data set, if you remember, is multi-resolution, so this won't return to me a two-dimensional array, because it can't. That two-dimensional array would have to be regularized to whatever the adaptive mesh refinement sets it at, and for SPH data sets, it would have to be regularized from a one-dimensional array into a two-dimensional array. So what we're going to do is we're going to take this, and this returns to us a slice object. And when we import widgets, which we did up here, up above, widgets does a a little bit of what I believe is called monkey patching, where it adds on a couple methods to slice objects and projection objects. One of those is the display method. So when I call s.display on density, you'll see that it brings up this navigation. And I want to point out that Widgets is a project that was developed in the community. A lot of the work was done in collaboration with Medik and Monk. I did a bunch of work on it. Nathaniel Clausen did a bunch of work on it. And some of the dataset viewer stuff was done by a graduate student named Xiaotong Hu. But what it does is it pops up for you this image. Now, this doesn't look like much. You see it's mostly purple. There's a little ring in there. So I'm going to go ahead and I'm going to log it. And now you can see right away, oh, wow, this looks pretty rad. What this does, and this is what I'm really what I really like about this, what it does is it actually passes the entire irregular mesh data set up to Jupyter. So it takes that two-dimensional, or that set of one-dimensional arrays, so the centroids, the widths, and the values, so 5 sets of values. It passes them up as a typed array into JupyterLab. JupyterLab then has access to them as typed arrays. And what we did was we ported some of the pixelization routines, so the routines that actually take that variable resolution object and turn it into an image, into that two-dimensional image. We took those that were developed in YT and Python, and we ported them over to Rust. And this was, Rust was the cool thing to do at that time, which was, a non-negligible fraction of why we decided to do it. And we then used that to cross-compile it for WebAssembly. So what that means is that we generated WebAssembly routines, so fast, near-native performance routines that could take our two-dimensional arrays, or one-dimensional arrays, and turn them into two-dimensional images. So the end result of this is that every time I click and drag and move or zoom or whatever I do, it doesn't communicate with the server. And that's key. It is passing information, but it's not. It's passing information about the location, what I'm looking at, and so on. But all of the generation of images happens here on the client side. So as I'm clicking and dragging, none of that is happening on the back end. All of it is happening here. And some of the neat things about that are that you get really much faster response rates. So instead of passing, oh, this is my new viewport, so generate for me a new image, and then having that image get turned into something, that adds latency, it adds processing time, it adds a whole bunch of things if we were to do that on the server side. So instead, we're doing them at near native speeds here on the client side. And we've got some zoom buttons here, so this is a very Wayne's World thing to do. There are a couple issues that haven't quite been sorted out. Like if I zoom with my scroll, it doesn't modify that. And it also applies the color map and the normalization and so on all here inside the browser. So I'm really happy with this in the sense that this means now we can generate an image one time on the server, or not an image, we can generate a slice or a projection or any of those variable resolution objects on the server, and then we can pass them back to the client and basically do infinite exploration of them without having to connect with the server again. Now, if you're watching carefully, you'll note that up here, this flashes every time there's a thing, and I think that it might be communicating with it might be sending data about where my mouse is positioned to the server, because I think that we've got a query, but it's not communicating with the JupyterLab kernel to do anything to do any of the image generation. And this works with not just slices, but also projections. So if I make a projection, so ds.r, and here I'll just grab all the data, and I'm going to integrate it. I'll integrate the density along the x-axis this time. And I'm going to say p.display density. Now, this is a projection along the x-axis of the density. Doesn't look like too much, so let's go back up here, and instead of projecting along the x-axis, let's project along the z-axis. And now this is our same data set. but instead of slicing, we're projecting. You can see that you do get a bit of a different, a different set of values. And this is the column density because we're integrating. Now, if we were to take the mean and weight it with something, then that would be, another way to look at the data. Okay. So that's where widgets is today. We have this interactive slice viewer. Oh, nice to see you, Clement. Yeah, it's super fun, right? Unfortunately, it doesn't yet work on cylindrical data, so we can maybe port that over to Rust at some point too, and cross-compile for WebAssembly. But it does work with all the Cartesian data. So the combination of these different things allow us to really get at our spatial positioning in our data set. And one thing that I didn't really talk about was that we've started exploring adding on additional components here. So for instance, this domain viewer. There's no reason that you can't take an image like this and connect it here. And that's something that we've looked at. So having textures here be mapped onto either textures or typed arrays that are generated inside other viewers. But getting the user interface for that just right is certainly something that we're thinking carefully about before doing anything else. The other thing is that I've been exploring adding in particle rendering here, but as of right now, I'm not super pleased with the performance I've been able to get out of it. And again, that's probably my fault, not the fault of Py3JS or WebGL or anything like that. But maybe in the future, we'll have the ability to do some particle rendering inside our dataset viewer. Right now, it's mostly optimized for AMR, although the SPH datasets, if you properly construct them, would work with both of these. So that's one of the fun things that I wanted to show with widgets. And widgets is available on PyPI. You can actually just do pip install widgets, and you'll get it installed, and it should work right there with Jupyter Lab, and you should be able to see it and run it. Thinking about the future, we're hoping to add on some more features to really dig into different ways that we can make interactivity accessible in it. So I'm going to pause for just a moment to take another sip of coffee. Okay. So the other thing that I wanted to start out with today is I wanted to start out with looking at some of the things that have been going on in what we call YTIDV. So YTIDV is, and I'll show you the page for this. Both of these projects, their GitHub repositories live under the YT-project.org. YTIDV is an interactive volume renderer for YT. So this is based on raw OpenGL using, I want to say, GLFW. It has a GUI provided by Dear IM GUI, and it's designed to provide basic access to OpenGL volume rendering. There are a number of different components that you can add, although right now it's not the easiest to add all of them. And this is an example of it. A couple things about it. It does provide off-screen rendering, so you can use EGL. So that means that, for instance, if you are running on a large cluster of machines that are equipped with GPUs, you can do off-screen rendering on it. A side effect of that, which I haven't explored recently, so I'm not sure I'm going to try to demo it, is that you can also dump it directly back to a Jupyter notebook. So you can have something here displayed in Jupyter, and then inside that, have it be displaying something rendered on the server with OpenGL. I might try that on a little bit to show it to see if it still works. It's all based on the Traitlets library, which I believe originated well, it's certainly used mostly in Jupyter Lab, but may have originated in, or it's certainly used the most inside the Jupyter ecosystem, but I have a memory somewhere that it may have originated more closely with Matplotlib. And what it does is it allows for real data-driven updates to your scene. So I'm going to show YTIDV. So there are two different ways that you can run YTIDV. The first way is completely scripted. So when I say completely scripted, I mean you initiate a YTIDV session, it displays things, and then when you quit, it terminates your Python session. This is fine in some cases, and it certainly does provide the best performance from the perspective of threaded rendering and so on. So running YTIDV looks something like this, and I'm going to make my font a little bit bigger. We import YT, we import YTIDV, and then we construct what YTIDV calls a rendering context. These, I believe, are the default values for it, but I'm not certain. So we construct a rendering context. We say our height will be 800 pixels, our width will be 800 pixels, and we want it to have a GUI. And then this is a fast way of just adding on a bunch of different components. I may talk in a little bit about what the different possible components are, but this will add on what's called a block collection and a block rendering. So YTIDV separates out the notion of data components and rendering components, as well as annotations. We'll talk about annotations in a moment. But here, we can run this script. You'll see that it ends with rc.run. So the way that GUIs work in many cases is that they require there to be an event loop, and then looking at other loops. And so this is where we turn things over from the Python interpreter to the event loop. So I'm going to run this. It loads up that same data set we were just looking at. Now, because I'm impatient, I have turned off ghost zones. Improving the speed of ghost zone generation would be a major improvement in YT, but unfortunately it's a tricky problem. And so it generates this GUI, and you'll see that we've got our GUI here. The GUI is a little bit finicky at times because we're integrating it with all these other different things. We're rendering it on top, and the way that the DRIM GUI works was a little bit confusing to me when I first implemented that. And I want to note that there's been a lot of work done on this by Chris Havlin and Aidan Sachowski. This provides to us our file name template. You'll see that takes what looks like format strings. And it gives us a couple drop downs, but we also get our standard orbit type controls here. Now, once again, the clipping plane stuff gets a little bit wonky if we look at it too much, but you can see that as I'm dragging it, I'm getting reasonably good performance here. It's not that big of a data set, but this is doing pretty well. And we have drop downs for debug, so you can save out the depth buffer because we were working on that for a little while. And then there's information about the camera position. This gets updated every time because it's all based on traitlets. And then this element of block rendering. So this lets us turn on and off things like the depth buffer, or displaying the depth buffer. And you'll see that it has options to change the color map. You could do Viridis, Magma, or everyone's favorite palette, Doom. Let's go back to Arbra. You can turn on and off the log. And then, because unless you manually set the color bounds, it will auto set them. You can also have it reset the color bounds. So if I zoom in, I can reset the color bounds and it'll compute the min and the max. It also helpfully outputs these, I believe, unfortunately, via a print statement to the command line. There's several different shaders that you can use. Right now, it's just using maximum intensity, but you can also do projective integration, where you'll also have to reset the color bounds. And then color transfer function, which right now, probably best not to utilize. Let's go back to projective integration. I'm not an expert on ISO contours, but look for a blog post about that coming up on the YT blog very soon. Excuse me. We can also do things like adding block outlines. And if we add a block outline, you'll see that that adds on all these different blocks to it. I'm going to turn that off now. Oh, that's the block rendering. I'll turn off the block outline. But you can turn on and off the block outline, and then let's see, you can bring the width way down. You can also make it way bigger. Then we could also have kind of a wide one with low alpha. Anyhow, that's a bit of a, a bit unnecessary. And this is useful in some cases to do some exploration of the data, but where it becomes more useful, oh, looks like I've still got some events printing out here, and I think that's actually in my Piglet installation, is when we start to use this to look at subsets of data. Thanks, the Mr. Josh. Have a good one. If we look inside the examples directory, let's see if I look inside it, there's a whole bunch of different things in here. One of the ones that I want to show is this Amr Subset Sphere. So here, if we look at our Amr Subset Sphere, here you'll note that I'm doing something very similar to what we had seen before. Let me pull these two buffers up so you can see them. In the first one that we were doing, we've got this load sample for isolated galaxy, and then we just add scene and we add that data set to it. In this other one, we create a sphere, and then we add only that sphere to the rendering. So in the second instance, this new one, what YT does is it computes like you would expect the sphere data set, or the sphere subset, and only that is the data that gets added to the scene. So here, instead of rendering everything, it renders only that Amr subset based on the sphere. So let me go ahead and run this example. And here you see, yeah, it looks like we've only got that sphere. So this provides a couple advantages. One advantage it does not provide. It does not provide an advantage in terms of scaling the data set to the view. That's something that I worked on for a while and was never really able to crack the appropriate nut. I think that there's probably something straightforward about it that I'm just not getting, but getting the scaling to work self-consistently inside the various different renderers and shaders and whatnot was beyond what I was able to accomplish. So if folks want to do that, there is a Vertex Scaling branch that never really finished. This provides us, though, the ability to only upload a subset of our data. So if you have a large data set, you can utilize this to upload only utilize a subset of your GPU's memory. So if you have a data set that would not fit inside GPU RAM, then you can use the subset here, so adding a scene using just that in order to provide a much smaller set of data to it. So there are a bunch of other cool things that you can do here, and I'm actually not seeing my examples. Oh yeah, we've got examples of how to run things off screen. So here we've got import YT IDV. Instead of allowing the default for render contexts, I provide it EGL as our render context, and I add my scene with all data. And you'll see that now I run a run command, and then I'm commanding my camera to move forward, and then I run it again, and I write out the bitmaps each time. So if I do this, Python examples AMR off screen, assuming it doesn't break, it will do the entire rendering process without popping up a window, without mandating that there's a GUI present, and then it will output onto my into my current directory these two different files, step1 and step2.png. Let's see what they look like. There we go. So I've rendered off screen without requiring that I have X11 forwarding or anything like that. And that's actually how the Jupyter Lab stuff works as well. There's an example notebook in here, I think. IDV widget, where what it does is it utilizes basically the same thing, but instead of outputting the PNGs to disk, it puts them into an image widget that shows up here, so you can interactively modify and so on. And since I'm feeling a little, I guess I'm feeling a little optimistic. Let's see if it'll work for me. So this is the IDV widget. I'm in the wrong kernel. So now I'm adding the scene, I've got the render context, and there we go. We've got an add image. Now, I mentioned before that this is all, data driven in the sense that it, when any of the values that correspond to, say, how it's updated, how the view is computed and so on are updated, it regenerates them. So now if I type rc.camera, was it camera? rc.scene.camera. If I type move forward on it, and I say 0. Well, let's do 1.5. That's what we did over here. What should happen is it should move the camera, invalidate everything, and then update the image. Seems like it didn't though, so let's try rc.run. Now it updated the image. So we can move our camera very, very deliberately. So let's see, rc.scene.camera. Let's see what we can do on that. We've got things like setting the far plane, the focus, the FOV, the orientation, update orientation. Move forward is certainly the one that seems obvious. So why don't we instead, here, let's rc.scene.camera.move forward, -1.5, rc.run. You see now we're back to where we were before. So we can do some cool stuff with that. We can do things interactively. But the thing that I haven't shown yet is something that I'm kind of excited about that, well, we'll see if I can make it work. So that's a great question, Stuart, and that's exactly what I was going to show. So here inside, so let me go back to AMR volume rendering. I'm going to comment out rc.run. So IPython provides a whole bunch of different event loops. So these event loops require things like setting up a primary application instance, querying that application instance, sleeping for an amount of time to see if there's an event, updating it, so on and so forth. But they're a little bit clunky at times. Because we're using the GUI framework Piglet, and IPython knows about Piglet, we can use IPython's knowledge to provide an interactive prompt while we are utilizing it. So here I'm typing IPython --GUI equals Piglet with a Y, and then I'm saying -I examples AMR volume rendering.py. So it's generating everything, is tossing it all up onto the GPU, and you'll see now we have this, but we also have this. So here we've got our entire scene graph object, and we can modify it as we're going through this. So if I look at sg.components, you'll see here there's a block rendering. I can add on a grid outline to that. And now, if I type sg.components, you'll see down here, there's also a grid outlines. Now, for some reason, these are in reverse order here, and I'm not totally sure why that is, but that also means that we can do things like add annotations. So for instance, I can add a box, I can add text, I can add a volume, I can add all those different things. So for instance, if I want to do sg.addText, and I can't remember the text equals that, origin equals that, okay. So sg.addText, and I want my origin to be, let's say 0.05 and 0.8. Here you'll see that it has added that. Now it takes y and then x, so it doesn't quite work the way that I want it to, but we've now got an annotation right up here. One of the neat things you can do with that text annotation is equal to that. I can change the, let's see, what is it? Is it text? Yeah. I can change the text and it goes ahead and it updates the annotation there. So for instance, you can have it update and have like a key or something like that that shows what you're looking at, or you could even have it describe the position or the zoom or something along those lines. So this is with the event loop running, where we've now got interactive IPython. In the past, I've had issues with some weird interaction causing seg faults if I try to do too much tab completion. So it's not perfect, but it is kind of fun in that sense. And this also allows you to open up, or it also allows you to do some cool stuff that would have been kind of clunky to build a GUI around. So let's take a look at sg.components 0. You'll see that's our block rendering. So I'm going to say br is equal to sg.components 0. We have a couple handy functions on br. These are all demonstrated, I believe, in the documentation too, I want to note. It's not br. bc. So sg.components, sg.data objects 0. So bc allows you to look at, so the way that the data is uploaded, and this is how things like spheres and other subsets are handled, is it's uploaded with, and let me get rid of this grid outline thing. Okay, visible, yeah. Ooh, text annotation. Oh yeah, we don't really want that. That's not updated. That needs to be fixed. BC allows you, it uploads along with the actual data that it's rendering, it uploads a bitmap. And that bitmap provides information about which, that bitmap provides which cells should and should not be rendered. That's how we do things like doing subsets of the data sets. And also, Stuart, if I didn't answer your question appropriately, please ask again, because I thought that I did. But and one other thing I should note is that the rc.run knows whether or not to exit also based on the render context. So EGL, it knows not to exit. But the Piglet one, it knows that it should. And I think there's also a Mesa one. But so we can modify those bitmap values as well. So for instance, we can do that with something like a filter callback, where you provide a filter callback, but that's a bit clunky. So we can say, for instance, no, filter callback is what we want. So we can say filter callback, and we can provide to it a function. So let's take a look at what exactly we're looking at, what we might want to do. And I'm going to take a look at the docs here just so that I don't make myself too silly. Guess it's not even in there. Okay, we can provide a filter callback. So I'm going to define a callback, and what this does is it calls our filter callback for every single grid, and it gives us a bitmap. So whatever we return gets uploaded back to the uploaded back to there. So this accepts a grid object, and so I can say I just want grids where the temperature is less than 10 to the 5. Yeah. So here I've said, oh, I didn't actually return anything. So I can say return wherever the grid temperature is less than 10 to the 5 Kelvin. So if I now do bc.filterCallback and I provide it with that callback, it goes through, it computes everything, and in principle, it filters that. Although it looks like it didn't. All right, let's try one more time. Grid temperature less than 2. Yep, so it did. It's just that there wasn't anything, or there weren't that, it previously wasn't a good distinction. So whenever you apply a new callback, it doesn't provide the logical, it's just that callback. So here, let's do everything less than 10 to the 4. So now we've cut out everything where the data had a temperature less than 10 to the 4. So this lets us apply, filters and so on and so forth. Not quite as interactively as we would like, but reasonably interactively. And I actually thought that I had helper functions that were like, filter this field above some other thing, but apparently I don't. So to wrap up the YT-IDV stuff, we've got a couple different sets of annotations that you can provide. You can provide a box, a text, you can provide outlines of different components. We have components as well. So what I didn't show is I didn't show SPH rendering. SPH rendering isn't really working that well. I'm not super duper happy with it, but it does kind of work. And it does produce results that aren't, well, if I'm remembering correctly, they aren't that terrible. But that's something that we've been working on. Thanks to some work by Corentin, we will probably have octree blocks rendering reasonably soon. One thing that I didn't show that I think I actually would really like to take just a moment to show is that we also have the ability to update shaders on the fly. So let me go ahead and I'm going to unfilter this. So let's say less than 10 to the 10 Kelvin. So that should give me everything, and now I'll apply that filter. So when we look at this, we see these different shaders. There's a recompile shader button. What the recompile shader button does is it reads the shader off of disk. We provide support for, I think, just 3 types of shaders: a fragment shader, geometry shader, and a vertex shader. And in general, we just use the vertex and the fragment shaders. The most interesting ones are the fragment shaders. So we have a base level ray tracing fragment shader, and maybe it should be called something different, but what this does is it walks through a grid of data, and it calls a sample function at every single point, or multiple times inside a given cell. That sample function is provided by some other shader. So for instance, max intensity looks like this. This computes the maximum intensity of our data set, or at every single pixel in our visualization. This is all that you have to write, and I know it looks like a lot, but this is what you have to write in order to compute a new volume rendering set of values. So for instance, if instead of wanting our current color to be just the value of the texture, if you wanted it to instead be the gradient of the texture, or if you wanted to offset it with a secondary value, you would just have to write something like this, and then you could modify it. And the neat and fun thing about this is that we can have it recompile them on the fly. So if I'm in here and I'm editing this, and let's say that I've got this integration, so let's go over here to my projection shader. Let's say that instead of multiplying each set of values by the t delta, I want to multiply it t delta. Let's square t delta. So when I call projective integration, I recompile, I reset the color map, and it looks like that. Now if I undo that change and I recompile the shader again, you'll see that it rereads it off of disk and it recalculates it. Now, there are probably better ways that we could, faster, more iterative ways that we could do that, but this allows for what I think are pretty cool ways of really quickly experimenting with what you can do tracing rays through a domain. So if you wanted to, for instance, have multiple different fields that were uploaded, that's certainly something that you could do. You could upload multiple fields and then have them combined in some strange way. And this is all feasible while still not having to quit the application and reload everything from disk and upload it back onto the GPU. You can also experiment with other things, like, for instance, we could do something. So a common thing that I've seen people do is construct, specified isocontour shaders, where you're saying, I want this width at this value and so on. And that's something that can be done with a transfer function, but you could also do it directly inside a shader. So I like that aspect of it as well, because it also makes it a lot easier to experiment with things, especially if you're doing interesting things with geometry. So that's basically what I wanted to show for these different things. And you'll see that here I'm running this interactively. And one thing I didn't quite mention was, though, that running this in the event loop in IPython adds on some oddities. And I don't know if you're seeing the artifacts here that I am, but that's because this doesn't necessarily trigger a redraw of the a redraw inside the application. So that means that we get little bits of operating system gunk and so on, which I think is less common if you're not running inside the IPython event loop. The other thing that happens is our refresh rate here is slightly, not incredibly, but it is slightly worse than were we running it, and I believe that's because of all the latency from having to check the event loop and so on, and calling into Python and whatnot. Now, it's not terrible, but it is there. One last set of things I want to show before I conclude. We have this file name template up here. There's also debug and camera, and I think I alluded to those earlier. But this file name template lets us save out images. So I'm going to save a snapshot. And then I'm going to zoom in a little bit, save another snapshot. And I'm just going to keep saving snapshots. And now I'm going to quit out. You'll see that it saved out all of my snapshots. Now, you might think to yourself, I don't want that ugly GUI on top of them. Well, the GUI is drawn in its own separate step. So when we save out a snapshot like that, it saves everything that is rendered except for that GUI. So you can use this to generate values and to output images from those values. It's a little bit tricky to get the color bar, but that's something that we're working on. But you can do this, and honestly, I think this is a pretty fun way to explore your data sets. The last thing that I'll say is that you've probably put together that it should be possible to export your point of view here to the camera, and that is possible. I'm not going to attempt to do it right now, but I have done it in the past, and I thought that the example was inside the repository, but it's not. And so in principle, where we want to get to with this is that if you have a rendering context on screen, being able to have dynamic updates of your position here automatically update a rendered image that's done using OpenGL on the server. So logging into a remote system where you maybe have a big piece of data, running a kernel on the compute cluster, but then rendering the GPU-based volume rendering there, while looking at the locally rendered GPU-based 3JS and using that to interact with it. So that's what I wanted to get through today. This package is also available if you pip install YT_IDV. Oh, and I think I only mentioned me, Chris, and Aiden, but Clement has also contributed to the repository. This is a package that we continue to develop, and there will be a blog post going up soon because we've been implementing some other things that I'm excited about that Aiden has worked on. But yeah, that's what I wanted to go over today, with some cool interactivity that I don't think people see as much with YT. So I hope that that's been useful for you. If you have any questions, feel free to drop by the Slack, but thank you very much for coming today. I think I'm going to go ahead and shut down the stream in just a moment. So, thank you, everybody.